One example of constant acceleration is the acceleration due to gravity. And basically, if we take an object like a tennis ball and we hold it above the surface of the earth and we let it go, it will accelerate downward with a constant value. And we say that the object is in free fall when it's under the influence of gravity. Some of the things that we consider when we look at gravitational acceleration is that the object is under perfect conditions, which means that we have to assume that there's no air resistance or friction. And we also have to assume that the acceleration is uniform throughout the entire Earth, which it's not. Actually, the acceleration depends on where you're located vertically. So if you're at the top of a mountain versus at sea level, the acceleration will be slightly different. But because the acceleration is a constant value, that means that if you take an object and you release it above the surface of the Earth, or if you throw it up into the air and let it go, that object will speed up or slow down at a constant rate, depending on which direction that it's moving. The acceleration due to gravity is a value that is equal to 9.8 meters per second squared, and it's, like I said, it's uniform throughout the Earth, and at least we're going to assume that, because we do know that it does change, as I mentioned. So G decreases a little bit with altitude. If you're up in the mountains, it will be a little bit less. And it also varies slightly with latitude. But on average, we can say that the acceleration due to gravity is 9.8 meters per second squared. So what does that mean? That means that when an object is in free fall and under the influence of gravity, its velocity will change by 9.8 meters per second every second that goes by. So what does it mean for an object to be in free fall or moving under the influence of gravity? Basically, it means that the only thing that's acting on it is gravity, so there's no other outside forces acting on it. There's nothing propelling it. It's not like an airplane that has fuel and so on. So it has to be completely on its own, just acting under the influence of Earth's gravitational pull. The acceleration is always directed downward, regardless of the initial motion. So if I release a ball and I drop it, it accelerates down towards the earth. It speeds up as I drop it. But if I throw it up into the air, it actually will slow down on its way up. So its acceleration is still directed down. And we'll see this a little bit more in a minute. For this particular presentation, we're going to use that the acceleration has a value of 10 meters per second squared, and so we say that gravity is actually 10 instead of 9.8. And this just helps with visualization, and we'll see why when we look at some examples and we try to conceptualize this. But the negative sign here just implies that the acceleration is always in the downward direction, right? It's directed downward. And we say that the positive direction for vertical motion is upward. All right, so here's a really quick question. So we take two balls, we release them both from rest at exactly the same height. The second ball is twice as heavy as the first ball. Which is the statements is true? Is the heavier ball going to hit the ground first, the lighter one hit the ground first, or will both hit at the same time? So if you've never seen this, there's a video that you can watch on YouTube which shows, I think it's Neil Armstrong on the moon with a hammer and a feather dropping both at the same time. And it turns out that in the absence of air resistance, both balls will hit the ground at the same time. And so here is an example. It's a little GIF file that sort of animates what we're talking about here. So intuition sometimes tells us that the heavier ball should hit the ground first, but it really doesn't matter. They should both hit at the same time. Now, what we're used to in nature, of course, is the fact that there is air resistance present. So what we see sometimes is not what we're seeing here. But if we performed this on the moon, where there's basically no air, then they would hit the ground at the same time. All right, so here we drop an object in the absence of air resistance. We know that it accelerates downward, so if I take a tennis ball and I let it go, it's going to accelerate downward at 10 meters per second squared. So this is asking if instead you throw it downward, what's going to be true about its acceleration once it leaves the hand. So I stand on the top of a building and I throw the tennis ball straight down, what's true about its acceleration after it leaves my hand? And the answer is that it's still exactly 10 meters per second squared, or negative 10 meters per second squared. So the acceleration due to gravity is always the same value. The only thing that's different here is that your hand is giving that tennis ball some initial velocity when it leaves your hand, but then gravity takes over, and whatever velocity it had, the velocity would then change by 10 meters per second every second. Same sort of question. We throw a ball straight up in the air at 5 meters per second. After it leaves your hand, still exactly 10 meters per second squared for its acceleration. So the idea here is that basically once gravity takes over, the object is always going to accelerate at the same rate, and it's always going to be a downward acceleration of 10 meters per second squared. All right, so let's think about what's happening if I drop an object under the influence of gravity. So I have an object here like a ball, and I'm going to release it at a time of 0 seconds. And what I'd like to do is I'd like to look at what's going on with the motion after every second that goes by. So I know that I have a downward acceleration of 10 meters per second squared, where the negative sign is telling me it's downward. I know the ball is moving in the direction of the acceleration, so I expect that the object should have an increase in its velocity because the motion is in the same direction as the acceleration. And so after 1 second that goes by, the velocity will have changed by 10 meters per second. So after 1 second, it's traveling at negative 10 because it's traveling downward. After 2 seconds, it's going to be negative 20, so the velocity has increased by another 10 meters per second. After 3 seconds, the velocity will be 30, so every second that goes by, the velocity is increasing by 10 meters per second, and it's in the direction of the acceleration, so it's speeding up. And it's also covering more distance every second, as we saw in the past with acceleration. Suppose we do the opposite and we throw an object up into the air. So we've given the ball, the object, some initial velocity of 40 meters per second. Once it leaves our hand, it's traveling at this speed. We know that gravity is still acting downward, so the acceleration vector is opposite the direction of the motion, so we should expect that the velocity will decrease. And so every second that goes by, the velocity changes by 10 meters per second. So after 1 second, it's only going 30. After 2 seconds, it's only going 20. At 3 seconds, it's going 10. And at 4 seconds, it's going 0. So at the very top of an object's trajectory, when it's traveling vertically upward, the velocity at the very top for an instant in time will always be 0. And this can sometimes appear as hidden information in a problem if it just says, I throw an object up at 40 meters per second. How long does it take to reach the top of its trajectory? Well, it takes 4 seconds, but the hidden information is that the velocity at the top is 0. And we'll look at an example of this. All right, so it's at the very top. So it traveled all the way up. It got to the very top, so that's where it is at 4 seconds. But now it has to fall back down again. So when it starts to fall back down, it basically behaves as if it was dropped. It has the same conditions where it was starting off at that 0 velocity. So as it falls back down after 5 seconds, right, it's because it was at 4, the speed is increased to negative 10, and then 6 seconds, negative 20, and so on, and the speed keeps increasing. And then it gets back to the point basically where it was thrown. So here is a picture. I realize I switched that slide very quickly, but here is a picture of, this was the upward motion that we had, right? So we started off at 40, it went all the way to the very top. When it reached the top at 4 seconds, it was traveling at 0, acceleration was down, so here the acceleration vector is opposite the velocity vector, it's slowing down, and then it falls back down over here. And so here is the acceleration is in the same direction, it speeds up as it's going back down. So this is animated, so this is where it starts, and then after 1 second, 2 seconds, 3 seconds, then it reaches the top, then it falls back down, 5 seconds, 6 seconds, 7 seconds, and 8 seconds. So one of the things that I wanted to show with this picture is some of the symmetry in the motion between the motion going up and the motion going down. So one of the things is that at any given height, the object has exactly the same speed, different velocity because the direction upward is positive, the direction downward is negative, but at any given height, on the way up versus the way down, the object has the same speed. So if I go up here, they both have 20, both have 10, and when the object returns to where it started, it has the same speed that it had when it was thrown up, of 40 meters per second. Not the same velocity because the velocity is directed down. The other symmetry in the motion is the time it takes to reach the top of its trajectory is exactly the same amount of time it takes to come back down. So here it takes 4 seconds to get to the top, and it takes the difference between 4 seconds when it was at the top and 8 down here, which is another 4 seconds to get back down. So the total amount of time in the air is just double the time it takes to get to the top. So there are some symmetries in the motion that we can use if we're trying to solve problems. So just sort of a summary of what we just looked at. If an object is giving some initial velocity in the motion, the ball will slow down at 10 meters per second every second going up. It'll speed up at 10 meters per second coming back down. The time it takes to reach the maximum heights equal the time it takes to come back down again. Speed at any height is the same. We talked about that. The distance covered each second on the way up. It covers more distance on the way up each, excuse me, I'm saying this wrong, right? Object covers less distance each second on the way up, so it's slowing down, and it covers more distance each second on the way back down. Velocity at the highest point is 0. We talked about that. And the acceleration, no matter whether the object is thrown up or coming back down, is always negative 10 meters per second squared. So it's always going to be that value. The other thing that's actually interesting for us to determine is how much distance does the object cover. So we'd like to know if we were to release an object from some height, where will it be below its starting point after some time interval? And so it turns out that we can determine the distance covered from the time of release by using the formula that the distance covered is 1/2 gravity, and gravity here is not negative, it's just the 10 meters per second squared, multiplied by the time squared. So if we start off here at the top of our trajectory and we release this object, after 1 second it's going negative 10 meters per second, and we can calculate the distance that it fell from this starting point to this point down here. And that distance is 1/2 10 meters per second squared times 1 second squared. That's 5 meters. So that means that if it starts off at 0, after 1 second, the object has fallen 5 meters. We can do the same thing after 2 seconds. So if we go back to the starting position, we say how far from this starting position does the object end up after 2 seconds? 1/2 gravity, 10, times 2 seconds squared is 20 meters. So that means that the object has fallen from the starting point after 2 seconds, 20 meters. And we can keep going with that, right? So after 3 seconds, the distance is 1/2 10, 3 squared is 45 meters. So between the top and after 3 seconds, the object has fallen 45 meters. And then finally, after 4 seconds, it falls 80 meters, and we could keep going with that. But one of the things we do notice is that the object covers more distance every second that goes by. So during the first 1 second interval, the distance covered was 5 meters. Between 1 second and 2 seconds, right here, the difference between 20 and 5 is 15. The difference between 3 seconds and 2 seconds, between 3 seconds and here, this distance is the difference between 45 meters and 20, and then the difference between 4 seconds and 3 seconds, so this distance right here would be the difference between 80 and 45, which is 45 meters. So over time, the object is covering more distance every second. So the first 1 second interval, it covers 5 meters. The next 1 second interval between these two is 15, and then 25, and then 45, and we could keep going. So the object is definitely speeding up, and it's covering more distance every second. But we can use that fact to figure out how high an object would rise if it's thrown up, for example, if we know the time that it takes to get to that position, because the time it takes to go to the top is the same time it would take to come back down, and we could figure out how much total distance the object covers.